Welcome to Captain Sherry Classroom. In this video, we break down free surface effect and free surface moment. Let's get started. Free surface effect refers to the tendency of liquids in partially filled tanks or compartments to shift when a vessel rolls or pitches, affecting its stability. If this is the ship's transverse section, let us assume that the ship is floating in still water at upright condition and this is the waterline. The double-bottom tank is partially filled with water, and let's say the center of gravity of the water inside the tank is here, and we will mark it with a small letter G. If this is the ship's centerline, and this point is the ship's center of gravity, marked with capital letter G, where the total weight of the ship acts vertically downward. The geometrical center of underwater volume is the center of buoyancy, marked with capital letter B, where the buoyancy force acts vertically upward. For a ship to float, the buoyancy force should be equal to the total weight that acts vertically downward. When a ship tilts or rolls, the ship's center of buoyancy, capital B, moves to some point at the low side to be 1. The liquid within a partially filled tank tends also to move to the lower side, causing a shift of the center of gravity of water inside the tank. As small g moves, the vessel's center of gravity, capital G, also moves parallel to the movement of small g. Let us replay this animation again, how the ship's center of gravity moves together the center of gravity of the water inside the tank and the ship's center of buoyancy. Now the point where the buoyancy force and the ship's centerline intersect is called the transverse metacenter, capital M. And the horizontal distance between the ship's center of gravity, capital G, and the vertical line of buoyancy force is called the righting lever, GZ, which determines the ability of the ship to return to its upright position when she is tilted. This is supposed to be the righting lever if the water inside the tank does not move, or if the water is in solid form or frozen. But since the water inside the slack tank is free to move, due to its movement, the ship's center of gravity, capital G, moves in a parallel direction with the center of gravity of water inside the tank. Thus, the present righting lever of the ship at this moment is from G1 to Z1. If we extend the downward vertical force upward, intersecting the centerline, the point of intersection will be GV, or the virtual rise of the ship's center of gravity. The horizontal distance between GV to ZV is equal to G1 and Z1. The movement of the water inside the slack tank when the ship is heeled results in a decrease in the ship's righting lever. This is supposed to be the ship's stability triangle if the water inside the tank cannot move or the tank is pressed up, which is bigger compared to the stability triangle when the water is free to move inside the tank. The result is a reduction in the ship's stability due to slack tank. In this case, we can say that the distance between GV to M is the fluid GM, while the distance between G to M is the solid GM. The distance between capital G to GV is the virtual loss of GM, or usually we call it a free surface correction, or FSC. If we subtract the free surface correction FSC from the solid GM, the difference is fluid GM. According to the International Code on Intact Stability, it is mandatory for passenger and cargo ships that their initial metacentric height, or fluid GM, should not be less than 0.15 meter. I have made a separate video about GM, or metacentric height, and how to calculate the fluid GM. Kindly check the link in the description. So a ship with a partially filled tank or slack tank, when heeled or tilted at sea, will have a loss of metacentric height called a virtual loss of GM, also known as the free surface correction, FSC. As we know, by subtracting the free surface correction from solid GM, we can obtain the fluid GM. Where FSC is the virtual loss of GM, or free surface correction. FSM stands for free surface moment. Capital W is the ship's displacement. The unit of free surface moment is in ton-meter, while the unit of displacement is in ton. If both units of ton are cancelled, the remaining unit is a meter. That is why the unit of free surface correction is in meter. Usually, the unit of GM is in meter, so subtracting the free surface correction, which is in meter, the fluid GM is in meter also. This is the formula to determine the free surface moment, where small letter I is the moment of inertia, often termed as the second moment of area, and dt is the density of liquid inside the tank. Remember that the unit of the moment of inertia is in meter, raised to the power of 4, and the density is in tons per cubic meter. If we cancel both these units, we still have a remaining unit of meter. That is why the unit of free surface moment is in ton meter. For a rectangular tank, the moment of inertia is equal to the length times the breadth cube divided by 12, where I is the moment of inertia, L for the length of the tank, B for the breadth of the tank, and 12 is constant. Let us simplify this formula for a rectangular-shaped tank. GGV, or free surface correction, is equal to length times breadth cube divided by 12 times displacement, and the quotient will be multiplied by the density of liquid inside the tank. Thanks for watching. Keep learning. Best of luck for your orals. Stay confident. Stay sharp.